Hello everyone, my name is Romain Hodé. I'm a PhD student from the Acoustic Laboratory of Le Mans in France and also with the aeronautical group Safran. And today I will present you the attenuation of zero group velocity long modes for the non-destructive evaluation of adhesive bonding. So why are we interested in the non-destructive evaluation of bonded aeronautical assemblies? There are two main points. The first one is concerning environmental issues, because as you know, currently, we want to reduce greenhouse gases emissions, and so aircraft structures have to be as light as possible. And one solution to face this issue is to use adhesive bonding compared to other assembly techniques like, for example, welding or rifting, because in the case of rifting, you need to add some rivet to the structure, so to add mass. But on the other hand, we have some safety problems because currently we don't have a non-destructive method to certify the mechanical strength of the bonded assemblies. And this is a current technological limitation that we want to overcome. So this was concerning the context, but now the main goal of this work is to find a non-destructive method to determine if the bonded assembly is nominal or degraded. So we have manufactured 5 different samples, which are all composed of 2 aluminum plates that are bonding together through a layer of an industrial adhesive. So we have here the nominal case, here the case where we have the curing time of the adhesive that is about 50%. And we have 3 different cases with the addition of a layer of freeze agent. So at the first interface, the second interface, or both interfaces. And this layer of freeze agent is used here to degrade the practical adhesion between the medium and the adhesive. So the samples are, can be discriminated with conventional NDT method. So that's why we want to use laser ultrasonic method, because this method is really interesting, notably for an industrial point of view, because this is a contactless method. And also, this method is non-destructive if we stay in the thermoelastic regime. And we want to use zero group velocity long modes because they are really interesting, as I will show you after in the next slide. The ZGV mode allow to have local measurement and really high sensitivity, as it was pointed out by Silva Mesil in this article concerning the non-destructive evaluation of adhesive bondings, and notably concerning the study of the frequency of the ZGV modes. And in our work, we will be focused on the frequency of the ZGV mode, but also the attenuation of these resonances. So now, concerning the theory about ZGV modes, if you consider a plate here, you will have the reflection of transverse and longitudinal wave at both free surfaces. And this multi-reflection lead to long modes, which are symmetric or antisymmetric modes. And you can represent these modes on this diagram as a function of the frequency and the wave number here. And you can plot the dispersion curve, so in red and in blue. And you can observe that at this point, the slope of the curve is equal to 0. So this means that the group velocity is also equal to 0. And we will have ZGV resonance at this point for this specific frequency and this specific wave number. So this is in about theory, but experimentally, what we can measure is this kind of temporal signal for an aluminum plate. And you can clearly see that we have this frequency here that correspond to the ZGV resonance frequency around 2 megahertz that correspond to this point in the dispersion curve that are obtained numerically. And this ZGV resonance around 6 megahertz correspond to this point in the dispersion curves. And now we can also plot the dispersion curves for 2 aluminum plates that are fully decoupled. So in the case of just a single aluminum plate, we will obtain this dispersion curves. And in the case of a thick aluminum plate of 3 mm, we have these other dispersion curves with a ZGV mode around 1 MHz. But we can also mechanically couple these two plates with two distribution of interfacial stiffnesses, so normal and transverse, that are used here to model the adhesive. And we can obtain the dispersion curves for this mechanical coupling between the two aluminum plates. And the dispersion curves are plotted in red. And we can see that they are different from the case, for example, for just an aluminum plate in black here with just one ZGV mode. So in the case of a coupling between the two aluminum plates, we will have different ZGV modes and different frequencies. But the goal of this presentation is not to find this value of interfacial stiffnesses, but is to study the attenuation of ZGV resonances as a function of time to discriminate the different samples. And now I will talk about what we can obtain experimentally on these samples. So to carry out the measurements, we have used this laser ultrasonic setup, which is composed of a pulse laser here in green with a pulse duration of 10 nanoseconds, and two-wave mixing interferometer in red that is used to measure the normal displacement of the surface as a function of time. And now, concerning the experimental results, on this 5 sample, we have obtained these frequencies. So in orange here, you can find the case of an aluminum plate of 1.5 millimeters. So as I've shown you before. And the other curves are for the different measurements made on the different samples. And what you can observe is that, for instance, for the nominal case, we don't have a clear resonance frequency, but it's more like we have two close resonance frequencies. But I will come back to this observation later. So we want to use the frequency of the ZGV mode, but also to study the attenuation of these resonances. And thus, we have applied a bandpass filter on the temporal signals to filter the signals around the 2 MHz. And we can obtain this temporal signal after filtering. So in the case of an aluminum plate and in the case of the nominal case. And we can plot this attenuation as a function of the time, but in a logarithmic scale. And thus, we can clearly see that we have a good accordance between the experimental attenuation and the theoretical model that was developed by Claire Prada. And we can see that this attenuation is a function of the time and also of the parameter τ1, which is due to viscoelastic effect. But in this case of an aluminum plate, this parameter is really high. That's why we have mostly an attenuation as a function of time. But when we want to apply this model on the other curves, we can see that we have some discrepancy, notably for the nominal case. But when we come back to the first observation, that here we don't have a clear resonance frequency, but it's more like we have two really close resonance frequencies. When we add this on the theoretical model, we can add a cosinus function, which is due to the beating phenomenon between two really close frequencies. And these frequencies are separated by the factor delta omega. And what we can see is that we have a better agreement between the theory and the experimental measurements. And notably, we can access two interesting metrics, which are τ1 and delta omega, that can be identified with this experimental attenuations. And we can notably see that for the nominal case, the parameter τ1 is the lowest and the parameter delta omega is the highest compared to the case, for example, of an aluminum plate. So that was for when we have 5 different samples with 5 different treatments. But now we are interested in what will happen when we have one sample and 4 different areas in the same sample. and to do an image of the bonding. So here you have the sample, so with 2 nominal areas and 2 degraded areas. And we have made a scan, a 2D scan with this laser ultrasonic technique based on the attenuation of ZGV mode. And we have identified the different parameters. And you can see here that for the identification of the parameter delta omega, this parameter is the highest for the 2 nominal areas. And also you can also notice that here in red, you have the signal here that we have a frequency around 1.9 megahertz that will, we have a beating phenomenon now between this frequency and this frequency. And this can be observed with the attenuation profile here. So this is due to the beating phenomenon between these 2 frequencies that are really large. But we have not observed this frequency around 1.9 megahertz on the previous samples, and this needs to be fully explained. Maybe it can be due to the migration of the release agent during curing, or also to residual stresses in the bonding due to the different areas. But these are questions that need to be addressed in the future. So to conclude, we have manufactured 5 different samples with 5 different treatments, and we have studied the damping of ZGV resonances. And we can see that this attenuation are sensitive to curing time and layers of contaminants. And we have a possibility of quantification using the 2 metrics, tau1 and delta omega. And when we have 1 sample and 4 different areas, we can see that we have an apparition of a beating phenomenon for larger delta omega due to the frequency around 1.9 megahertz. So concerning the perspective, the first perspective could be to use a simulation tool with a 3-layer model to notably understand why we have this frequency in red here. And the more general prospect could be to use a laser ultrasonic method in the nonlinear regime in order to access nonlinear parameters that could be really interesting for the non-destructive evaluation of adhesive bonding. Thank you for your attention, and if you have any questions, I will be glad to answer them.